This is a video about P implies Q. Or we can say that in another way, if P, then Q. So let's start with an example. So suppose we've got the statement n greater than 3 implies n greater than 0. So this should clearly be a true statement, because whenever n is greater than 3, it should also be true that n is greater than 0. So if this is true, so if P is true, then Q should also be true. So if we draw a truth table, looking at different values of n, so if n is less than or equal to 0, both of the predicates are false. If n is between 0 and less than or equal to 3, then the first one is false and the second one is true. And if n is greater than 3, they're both true. So what we're seeing here is all possible true-false combinations except P true and Q false. So P implies Q is only going to be false if we start with a true statement for P and we end up with a false statement for Q. So when P is true and Q is false. So whenever P is true, we also need Q to be true. So if we summarise this in a general truth table, so the statement P implies Q will be true in all cases except for the case when P is true and Q is false. So if we're trying to prove a statement of the form P implies Q, so if we're trying to prove this is true, we need only worry about excluding the possibility that P is true and Q is false. So all we need to do is to assume P is true and show that Q must be true as well. Assuming P false is not necessary, because in both those instances, in both these rows here, the statement is always true. So we don't need to check that. So to prove P implies Q, we only need to show that if P is true, then Q is also true. So when you're proving a statement, P implies Q, your first line will always be, if you're using a direct proof, assume P is true, whatever that statement is. And then use some logical argument to end up with the statement Q is true. And once you've done that, you've shown that P implies Q is a true statement. Now, if we're using proof by contradiction, to prove P implies Q, then we have to work under the assumption that P implies Q is false. So that will be our starting point. So we assume that P implies Q is false. And of course, looking at the truth table again, we just scroll back up, that only happens if P is true and Q is false. So this only happens in one particular case, if P is true and Q is false. Another way of saying that is the statement P and not Q is true. So when working through a proof by contradiction, starting with the assumption that P implies Q is false is the same as assuming P and not Q is true. And that's a good place to start because that gives you something concrete to work with. So let's look at an example. So let's try and prove that for all integers n squared is even implies n is even. So we're going to use proof by contradiction. So let's assume the statement is false. And argue for contradiction. So that's a good way to start, a good sentence to start any proof by contradiction with. So what does that mean in this case? So i.e., that means we're assuming the negation of this is true, and as above, that's the same as assuming P is true and not Q is true. So there exists, so here we've got a for all statement in the original statement, so when we negate that, it becomes there exists an n in Z, and negating the implication such that n squared is even and n is not even, which means n is odd. So notice the implication now has become an and when we negate it. So that's what we need to work with, and this is, we're now going to generate a contradiction. So if n is odd, we know we can write it as 2k plus 1 for some k in Z. And then we're interested in n squared as well. So if we take n squared and work that out using this 2k plus 1, then we get 4k squared plus 4k plus 1. And we can rewrite that as 2 times 2k squared plus 2k plus 1. And now the reason I've done that is because now this is 2 times an integer plus 1. So noticing that 2k squared plus 2k is an integer, we've now shown that n squared can be written as 2 times an integer plus 1, and that means n squared is an odd integer. So we've shown that n squared is odd. But now we were working under the assumption that n squared is even. So we've now got n squared is even and n squared is odd. And that's our contradiction. So this contradicts our assumption that n squared is even. So remember, integer can't be even and odd. So hence, using proof by contradiction, the original statement must be true. So just spelling that out again, that means that for all n in Z, n squared is even implies n is even. And that's the end of the proof.